our integral test tells us that if we have some function f of x which is positive, continuous, and decreasing, not immediately decreasing but at least ultimately decreasing, it is going down, and the integral to infinity of f of x dx converges, then the series to infinity of some a sub n that's related to the f of x also converges. Or the other possibility is that if the integral to infinity of the function diverges, then the series is also going to diverge. And this test is really good for cases where you have obvious u substitution or integration by parts, or it's obvious that you can use an integral to see if it converges and then compare it to the series. It's also, I should note, it's not necessary that we start at 1. We could start at 2 or any other number. So let's take a look at a rather tricky example of a series that we can evaluate using the integral test to show whether or not it converges, like you might see on your exam. They're always trying to trick you with these. So let's be ready. Here we have the series from n equals 2 to infinity of 2 times the log of e to get to n, or the natural log of n. All of that over n to the third power. And we can see that our if we look at this as a function of ln of x over x cubed, or 2 ln of x over x cubed, we can see that it is positive. It's going to be decreasing along our interval beyond x equals 2. And so we can try to evaluate this with the integral test. And if the integral is convergent, then the series would also be convergent. So we could say that this is similar to, it's not equal to, but it's similar to, so we'll use our little similar sign. This is similar to the integral from 2 to infinity of, just pattern match here, 2 times ln, and now everywhere where we have an n, we're just going to put an x there. Ln of x over x cubed dx. And now, because we have our ln of x and we have an x, at least one x down here in our denominator, we can use u substitution. And if we let u equal to our ln of x, then we could also say that if we have any other x factors, then e to the u is going to equal x. And in this case, our du is going to be 1 over x, so we're going to have an extra leftover x squared down here in our denominator, so we might as well go ahead and say that e to the 2u is going to equal x squared. And we also know that our du is going to equal 1 over x. So let's just rewrite this here. I'm going to write this over here so we have plenty of room. We have the integral, and now because we are substituting u's, we're not taking the integral from 2 to infinity anymore. We're taking the integral from u of 2 to u of infinity, is the way I like to write it. So we have u of 2, just to remind ourselves that we've done u substitution. We'll have to substitute our function back for u when we get to the end. before we evaluate this here. U to the infinity of 2 times ln of x. Well, ln of x was just our u, so that's 2u up here. And we can pull out a 1 over x here, so we know that we have our du. And we're going to have, like I mentioned earlier, we're going to have an x squared left over in the denominator when we do that. Well, we know that x squared is just going to be e to the 2u. Alright. And we can rewrite this here. We can rewrite this as the integral from u of 2 to u of infinity. And I'm just going to put all of this on one line here. So if we have 2 times e, we had here and down here in the denominator we had e to the 2u, so I'm going to write e to the negative 2u. That just means that it would be in the denominator, times u du. And now we have a couple of different functions multiplied together. We have our 2 times e to the negative 2u times u, and we can use integration by parts for this. And the notation that I like to use for integration by parts is f and g prime. Some people like to use du's and dv's, but I like to use f and g prime just because if you've already done u substitution, then you don't have too many u's flying around. And then if as you see that we are going to do u substitution again, we might use v for something else. So we'll say that our u right here is going to be our f function, and this part right here, our 2 e to the negative 2u, this whole thing here, that's going to be our g prime. That is going to be g prime. So just pattern matching here with integration by parts, we know that this is going to equal f times g, not g prime but g, so we'll be taking the integral of g prime to get g, minus the integral of f prime times g. And I guess we could say that's going to be, du. And this we're going to evaluate from sum a to b. And I'll just go ahead and leave it kind of abstract like that, because we have, u to the 2, or sorry, u of 2 and u of infinity here, but just for simple purposes here, I'm just going to say that we're going to evaluate that on some interval from a to b. And we'll just leave that kind of open like that. So before we begin, we just need to figure out what g is going to be. So I'm going to go over here and we're going to evaluate the integral of 2 e to the negative 2u here. So I'm going to go over here and just evaluate if we have an indefinite integral here of 2 times e to the negative 2u du. Well, what if we know that if this were e to the x, how we would integrate that would just equal e to the x. So why don't we use u substitution again? Well, we've already done u substitution, so let's call it v substitution. So let's let v equal our, what's up in here in our exponent, negative 2u. And that means that dv is just going to equal negative 2. Well, we don't have a negative 2 right here, but we can manipulate this here, where if we just make this a negative 2, then we can just multiply this whole thing by negative 1. The negatives would cancel out in the end, and then we could say that we have our dv here. So this is just going to equal the negative integral of e to the v dv, and we know how to integrate that. That's very easy. That's just going to be negative e to the v, because anytime you have the integral of e to the v or e to the x, it's just going to equal e to the v or e to the x, or whatever it's raised to that you have the dv or whatever of. And we just substitute back for v, and this is going to give us, it's equal to negative e to the negative 2u. And we said that this is going to be our g value here. That is going to be our g value. So just pattern matching back here with our integration by parts that we did before. I'm just going to section this off here so we don't get too confused. This whole business here is going to equal, put it in brackets, our f is u, so that's going to be u. Our g here we said is negative e to the negative 2u, so I'll just put that in. I'll put that in brackets here so we can preserve our minus e to the negative 2u. And here we're going to subtract the integral of f prime. Well, f prime, if f is u, then the derivative of that is just going to equal 1. So inside of this integral here we just have g. So that's just going to be this. We've shown that this equals g here. So that's a minus. The minus and the minus are going to cancel out, but we'll just leave it like this for now, just so you can see how the mechanics work of everything. We put that whole thing in brackets, and we said that we're going to evaluate this from u of 2 to u of infinity. And we'll go back to our original upper and lower bound and do that at the end. So let's clean this up a little bit here. Here we have this equals, we can just bring the negative out front, negative u to the e negative 2u, and minus is a positive. The integral of e negative 2u du from u of 2 to u of infinity. And we have already evaluated, we have already evaluated the integral of g prime, which was this, but we have not evaluated for the integral of e to the negative 2u. So we're going to have to come down here and figure out what that integral is going to be. So just make a little side note down here. The integral of e to the negative 2u du. Well, if we let v equal negative 2u again, then our dv is going to equal negative 2, and what I didn't show up here is that there would be a du here. So we could look at it both ways. And we don't have a negative 2 here in our function. So if we want to just solve for du, then we would just divide both sides by negative 2, and that would get us that negative 1/2 dv equals du. Now you have to be careful when you do this kind of algebraic manipulation. I like to do it all or none. So whatever term you have over here, make sure that you bring the whole thing. Don't try to mince it apart and have part of this leftover expression over here and part of it stays over there. Keep it all or none. Either you have it on this side or you have it on that side with your respective dv, and either you're solving for dv or you're solving for du, and just leave it at that. It tends to be a lot cleaner that way and less error prone. So we're going to say that this equals, we did our v substitution, this is going to equal negative 1/2. I'm just going to pull the negative 1/2 out front of our integral. It's an indefinite integral. And now we have e to the v dv. We know how to evaluate this. This is just going to equal negative 1/2 e to the v, which is just equal to negative 1/2. Make sure that we keep that negative there. Negative 1/2 times e to the negative 2u. And again, I'm just going to section this off here so we don't get that mixed up with what we were doing earlier. So we've solved for this integral here. So when we just drop this down, this whole thing that we've been working on here, it just equals negative u e to the negative 2u, and we showed that this integral is just this. That's minus 1/2 e to the negative 2u, and that we're evaluating from u of 2 to u of infinity. And now, because we've gotten this far, we can plug back in for u. So just bringing this down, just section that off here so we don't get any of this confused with what's coming down here. This is just a continuation of what we started up there. This equals, well, this is our negative u. We said that u was ln of x, if you recall. U was ln of x up here. So we're going to put negative ln of x. And here we have e to the negative 2u. Well, this is going to be 1 over e to the 2u, and e to the 2u we said was x squared. So this is going to be over x squared. And this is going to be minus 1 over 2. And again, e to the negative 2u, well, that's just going to be x squared in the denominator here. And because we've plugged back in for u, what we had substituted with u, we can just go back to our original lower and upper bound here. So that's going to be evaluated from 2 to infinity. And let's see what we have here. Well, we have this that let's say that we were evaluating for infinity first. We have this ln of x, and ideally this would be written as the limit as t approaches infinity. But I like to just go ahead and jump to the chase and put infinity up here because it's pretty obvious what we're talking about. So this would be ln of t as t approaches infinity, or just ln of infinity over infinity squared. So we have infinity over infinity, and we could use L'Hopital's rule, or we could just use a little bit of intuition here. Let's use a little bit of intuition. Let's use our brains here. Let's say that we have our x and y axis, and we have our ln of x function, which is going to look something like this here. It's going to come, this is going to be the point 1, 0. 1, 0. And let's say that we have, the other function is going to be x squared. So this is going to be our x squared function. This is ln of x, and this is our x squared function here. So this is 1 and 0. Up here you're going to have the point 1, 1. And at ln of 2 is just going to equal 0.69 something or another, while x squared evaluated at 2 is going to be 4 up here. It turns out that these two functions, they never ever touch one another. These never touch. The curves never touch. So what you're seeing is that this x squared here, this is just going to continue. This is just going to continue straight up practically. It just shoots way up when you have increasing x squared terms. And our natural log of x here is just, it's going to increase, but it's going to increase much more slowly. So the closer and closer to infinity you get, well, this just becomes more like 1 over infinity. This x squared term is just going to overtake, it's going to overpower our ln of x so strongly that this whole thing, evaluated as t approaches infinity, or just evaluated towards infinity, is just going to go to 0. So hopefully you can appreciate some of the intuition behind that. Now, again, you could use L'Hopital's rule and you could verify that, but like I said, I find it's easier if we just sort of use our brains and realize what we're looking at there. So this is equal to, when we evaluate this is equal to 0 minus, this would also be 0. So this whole thing is just 0 when we evaluate this at infinity. Obviously, 1 over infinity squared is just going to go to 0 as well. So this is just 0 when we evaluate at infinity, minus this evaluated for our lower bound at 2. So this is just going to be, put this whole thing in brackets so we can keep our negative terms straight here. Negative ln of 2 over 2 squared, which is just 4, minus 1 over 2 times 2 squared, which is 4. 2 times 4 is 8. Okay. And we could simplify this even further. This is negative of a negative is just going to be a positive. This is just going to equal ln of 2 over 4 plus 1 over 8. And we could multiply this, the numerator and the denominator on this side, by 2, and we could put the whole thing over a denominator of 8 if we wanted to. If we wanted to boil it down even further. So this is going to be 2 times ln of 2, then we have our plus 1, all of that over 8, and let's see, if I plug this into a calculator here, this is just going to equal 0.298 something. So it's important to note that this is not going to be the value of the series that we started with. This is the value of the integral. But because the integral converges to some finite value, we know that our series is also going to converge. So there, and then we have a little bit of real estate here. Let's just write the series that we started with here. Therefore, our series from n equals 2 to infinity of 2 to the ln of some integer n over n cubed, this converges via the integral test. And let's see, just as a side note here, I thought this was kind of interesting. If you do want to take that extra step and just compare what the integral equals to what the series equals, because we're starting at n equals 2, then that means that our series is going to be greater than our integral. So we could say that our series here, and this is just pure curiosity talking here. So this is n equals 2 to infinity, 2 ln of n over n cubed. It turns